Hello, community. Today we have a brand new AI research paper about AI reasoning. And I have my own ideas about this. So let's start. And yeah, this was the original thumbnail. I started here the video preparation. Well, to be honest with you, this was the original thumbnail I wanted to have for this video because it is only here the core about the chain of thought encyclopedia. Now, my younger viewers might ask, what is an encyclopedia? It's a huge book, and everything you know about a particular topic, let's say chain of thought, you write into this book and then you put the book into a library. Now, I had the crazy idea to take this encyclopedia and integrate it into a self-learning AI system. So, my journey begins. Now, if you're not familiar with DSPy, no, it has nothing to do with the official AI paper we're going to talk about. I just need the context. If you're not familiar, this is here 2 minutes DSPy. If you know DSPy, skip forward 2-3 minutes. This is beautiful because it's not anymore about prompt engineering, you know? DSPy here by Stanford NLP Group, they say it is programming language model and not prompting language model. The prompting will be done internally by an AI, but you just code here if you want what you want your language model to achieve. So here, official, DSPy shifts your focus from tinkering with prompt strings to the programming with structured and declarative natural language modules. Modules will be very important. So for every AI component in your system, you specify now with code an input-output behavior, and we call this a signature. It's just a term, never mind. And select now a module, remember, to assign a strategy for invoking your language model. I will show you in a minute multiple modules. And then DSPy expands your signature into prompts and parses your typed outputs so you can compose different models together into an ergonomic, portable, and optimizable AI system. These are the official wordings from DSPy AI. Give you a very simple example here. You have your DSPy signature. You define here the input field and the output field, some section and some subheadings. Another DSPy signature, input field, output field, great, and then you design your DSPy module. This here is a class draft, an article. So you have now a module chain of thought, the outline, and a DSPy chain of thought draft section, and you do something with this. And then you just invoke it, and you give it here in the last line, you see here a specific topic like the World Cup 2022. Great. Or let's go here with agents. Agents are much more interesting because you have here, if you go here for a DSPy Python interpreter implementation, you have a search Wikipedia, you have a Colbert version 2, okay, and then you have some address, beautiful, and then you get three information back here from this Wikipedia page or whatever you define, and then you have a simple DSPy React module. Now React is easy, no? You define now, as I told you in your signature, exactly how it should be done, what should be done. So you have a question and you expect an answer. But this answer has to be in a particular format. It will be a float number. And you're allowed to use the tools, evaluate math that we defined here, and search Wikipedia. And then you just say, okay, so React question, what is a particular number divided by the year of birth of David Gregory, something of Canary Castle, and then you let it run. And DSPy is now more or less here a flow process. You set up, you code exactly what you want your AI to perform for you. The logical content flow, the module flow if you want, and you define the input-output strings if you want for single operation. This is it. That's all there is. The main intelligence, if you want, is, of course, the DSPy optimizer. You have something in the background that is now optimizing the system for you. But hey, complete AI is an optimizer. Remember, backpropagation and all of this gradient descent. So we have the same thing. If you want from compiler to C, now we have this here. Different optimizers are defined for you in DSPy. So for example, for synthesizing here, good few shot example for every module. You don't have to ask. This is done automatically. It's a routine. It's a module for you, like Bootstrap. Or, and this is now interesting, proposing and intelligently exploring better natural language instruction for every prompt. And if you're familiar with this is a simple module, DSPy MIPRO version 2, or you use here building dataset for your models. You do this with DSPy Bootstrap Fine-Tune. So you do have already predefined optimization routines for you. You see this here for a class rec. This is your DSPy module definition. So you have a number of documents and you have your DSPy chain of sort, which you define. You will get some context, some few short examples, for example. Then you will receive a question and the system should prepare a response to this question. Great. So you define here number of documents, whatever, you respond, and then you have your DSPy.MIPRO and then you compile it simply. That's it. You have a training data set defined, Bootstrap demos, great. So either you go here with a prompt optimization technique, or you can really fine-tune here the tensor weights of your language model that you defined here as the base for all of this DSPy in the background. If you're not really familiar with this particular point here of MIPRO, I would highly recommend this beautiful article. This is here by Omar Khattab. He is from Stanford, basis KTH Royal Institute of Technology, UC Berkeley, and I give you here a detailed overview of optimizing instruction and demonstration for multi-stage language model programs. So, DSPy.ai or have here a look at the original publication. Really helpful. Summary. What we learned? MIPRO here starts with the bootstrapping. So it takes your program, your flow that you designed here in the code, which may be unoptimized at this point, and runs it many times across different inputs to collect now traces, or let's say reasoning traces, of input-output behavior for each one of your defined modules in your code. Then, we're talking about optimization, it just filters those traces and it only keeps the good one. How does it do this? Well, you have defined a metric like an accuracy, an F1, or whatever you need for your particular problem. You define here let's call it a success metric. And given this metric, the system now filters out the traces and only keeps the good one. Now, MIPRO enters here the grounded proposal stage. Wow. So it previews your DSPy program code, your data you provided, and traces from running your program here, and now it uses them to draft many potential instructions for every prompt in your program. So you see the optimization program now, the machine starts to run, and then it launches here the search, and it samples here mini batches from your training set, proposes here a combination of instruction and traces to use for constructing now every prompt in the pipeline, and it evaluates the candidate program on the mini batches, and you get the idea. So it is simply another optimization problem. You don't have to care about the best prompt. You just let the code execute here with an optimizer, compile it, and you will get a result. But you remember what I told you? You have a base AI, no? GPT-4 or go with whatever you like. OpenAI, of course. But you are limited by, let's say, the reasoning capability in general by this language model or vision language model. So careful. You are within the limits here of your AI. Yeah, teleprompters. Remember, I have multiple videos on DSPy. A lot of people ask me, what are teleprompters? This is a strange word, yeah? Forget the word teleprompter. It is simply an optimization engine, you know? So what it does, it generates multiple prompt candidates from your dataset that you provided here by simply, you say, solve step by step, question to the answer. Or you say, provide instruction, or you say, use algebraic principle to derive a particular answer from the question. And then what happens in the teleprompter, it tests those prompts on the validation dataset, on the validation problems here. It's a set of problems you have hopefully defined and provided here for the AI. Then it selects the prompt that maximize now your specific metric, let's say the accuracy that you want to achieve, and then the teleprompter simply compiles the best performing prompts into reusable modules. And this is the beauty of DSPy. You can build modules, you can combine, you can switch, you can cross-relate, you can build real complex flow structures with those DSPy. You don't have to care about compilation. Teleprompter does this. You just say compile. Of course, DSPy can also auto-generate chain of thought traces for you if you go here with only your base LLM and you not provide any training data or any data to train the system on. But of course, then the performance only depends on the base LLM zero-shot capabilities. And if you go with a local, a small 4-bit quantized LLM, do not expect too much of a performance increase, no? Because you kind of lose here, in my simple mind, DSPy's core strength, automated prompt optimization via some modules via the teleprompter. And now, having this background, now let's come to the main paper of today. And as you see, published May 15, 2025. And here we have a beautiful publication by those authors. Thank you to the authors from CASE.ai, Carnegie Mellon University, LGAI Research, Nava Search US, and Cornell University. And they published now their idea about the chain of thought encyclopedia. And what they think, yeah, we analyze, we predict, and we control how a reasoning model will think. And you might say, hey, was not in one of your last videos that you thought about the new DeepSeek R2, the reasoning model version 2 by DeepSeek? How interesting that now a lot of people are analyzing reasoning models. Now, if you read the paper, you see it's a bottom-up framework for analyzing and steering language model reasoning. Yes, we are again in the old topic, how to optimize the intelligence, the reasoning capability, the causal reasoning capability, the logic deduction capability of AI. It is simple. It is absolutely simple. The main idea is to improve this by guiding it to adopt a more effective strategy, better reasoning strategy. So what you do? You train a classifier to predict which reasoning strategy a particular language model would use for a given input. And you have access to open source reasoning models, language models, so no problem running there the tests. Then you simply apply our good old friend Bayes' rule to estimate the likelihood of the correctness with each of those strategies. And then you just prompt the model to follow the most promising one. You just calculate here the best probability. There's a second point I'm not going to address in this video here. This is here some beautiful insights how the training data format, the way you present the training data in a particular format for improved reasoning will shape your reasoning strategy. If you go in a free format or a multiple choice format or in some template structure, will have, of course, this is the form how you present new knowledge and how new reasoning traces. This will be a pattern that will be learned and there are consequences. And you find all this if you read here this beautiful new AI research paper. But in general, let's say the Chain of Thought Encyclopedia is a multi-stage framework for identifying, organizing, and analyzing. And this is here in the beautiful word. They really now analyze the strengths and the weaknesses of diverse reasoning strategies in the chain of thought output strings. How they do this? One sentence explains it all. Chain of Thought Encyclopedia automatically extract diverse reasoning strategies from model and language model generated chain of thoughts, clusters them into some interpretable categories, and generates contrastive rubrics to classify reasoning behaviors. You want to see here simple visualization? This is here from the original paper. So you just generate some outputs of an LLM. Let's say you go with GPT-4 Omni or an open source model. No? So classification criteria, identification. You have now a second AI system that looks now at the answer produced by the first AI system. I'll show you this in a second. But let's stick here to the methodology flow. So you have an analytical perspective, you have an idea development, you have some reasoning type that is either inductive or deductive, you have a verification focus, and whatever. Just let the LLM run through this. And then you say, listen, I have now, I don't know, 100 or 1000 criteria. Now I want that you cluster them. So what we do, we put everything in a vector space, and then we go either with principal component analysis, or if you're a little bit more advanced and you are a subscriber of this video, you know we go with UMAP. And I have even 2 videos to go beyond UMAP. But anyway, you just find clusters, no? That have semantic similarities. Now it is interesting, is it just a task description similarity, or is it a solution path similarity? And as a subscriber, you know I have a particular video on this. So you have your clusters. And let's say the first cluster here is analytical perspective. The second cluster here, and the principal component here, if you have a 2-dimensional reduction, an idea development, or a reasoning type, or verification focus. Great. And then you say, okay, I compress this now. I find the center of gravity of this cluster. Here, there's the main core of this cluster. And you say, okay, this is analytical perspective, this is idea development, you get the idea. And then comes rubric generation. So simplest one is bottom-up or top-down approach. No? So from an analytical perspective, you say now, okay, you use an AI to find this and say, okay, this solution now that is somewhere is clearly a bottom-up approach. No? Strongly inclined to immediately whatever. Or you say, hey, this is a clear top-down approach, demonstrate the ability to first conceptualize the entire structure and then go step by step with a particular methodology, you solve the task. So you see, you build this. No, the AI builds this for you. And then you have simply patterns. You let the AI do what the AI does best. Develop, analyze, generate, synthesize patterns. Patterns from huge data sets. And you got a pattern analysis, report generation, and then you have here the reasoning pattern show a clear top-down approach, or this response demonstrates multiple thinking ways, or the given response demonstrates strong deductive reasoning, or verification is here driven by the data rather than just some theoretical hypothesis about the influx of, you get the idea. And this is done by the AI. 2 AI systems communicate with each other. Each AI has a particular task, and then you know exactly, maybe you have different AI from OpenAI, or you go here with Anthropic, or we go with Gemini. Since the system generates the answer for you, you can go on a machine-specific, if you want global corporation-specific, but also domain-specific and task-specific solution. So we are real close to DSPy in the optimization structure. And then you say, hey, for a particular task that you now know, you have tested out all the possible things, you say, if now comes in a task, a new query for, let's say, an OpenAI system, you say, the optimal reasoning pattern control that I performed already gives me now the information, hey, I use now pattern A to solve this particular problem that just came in by the query. You see, it is easy, it is simple. And yes, I thought, reading this, I can combine this with DSPy. It's not in the report. This is just, I will have some separate, at the end of the video, some separate section where I share my personal thoughts that were not published in the official report. But let's come back to the official report here. Yeah? So what we have, the AI generates now a chain of thought traces, no? Produces free-form reasoning chains. Hey, I recall that diamond is made of carbon atoms, you know. Wherever we have reasoning models, you can have access, if it's not a closed source, to the reasoning chain of thought sequences. You can have brainstorm, no? Diverse reasoning criteria. You extract now from here these reasoning traces, criteria. Let an AI do this. And the AI will tell you, hey, this looked like an analytical perspective, you know. It compared here the benefit of a top-down approach to a bottom-up approach. There are plus and negative, so great. And then you just do here, the AI does this for you, embed all this information because these are just human sentences and human sentences consist of words. And we have a subword tokenization or a byte pair encoding tokenizer. So we built here a high dimensional 1024 dimensional vector space. And in this vector space, this was built here as a semantic vector space. So semantically close related subwords are closely related in this space. We have here a cosine similarity we can calculate. We have a hierarchical clustering. We have similar strategies. And we build here exactly the clusters. Then we build our creative rubrics where we say, hey, this is inductive. So it builds conclusion from the examples, or deductive. It applies some general principle like, I don't know, the equation of motion. Then we classify now the responses. So chain of sort outputs are now labeled using these rubrics. So AI says, hey, this response by AI1 uses here a bottom-up reasoning with some iterative verification in the chain of sort reasoning traces. And then comes the beauty. Then we calculate probabilities. We calculate conditional probabilities. This is our good old friend from 100 years ago. Across the benchmark to find out the strategies that correlate best with the success. Because we have defined the success metric, the success criteria, and then this boosts accuracy by 12% or whatever. And there you have it. So then you train just classifiers to predict the best strategy for a given question. So you have then the insight, hey, for this particular mathematical problem that you query me, use now a structured verification. This is the best way forward. And it is real similar, if you use here a pure code generator, but here we are in a semantic space. And then you just prompt here the model to follow it. So give the model now a reasoning instruction how to solve the query. You say, solve this using a top-down approach. Start with the general principle of fluid dynamics, add a little bit of mathematical understanding here of fluid vertices, and then break this down into some numerical calculation steps, run a numerical C++ simulation on the mainframe, and then deduct here, and So we have here defined a solution to a particular problem. If you think this is just me talking, you're absolutely right. You should go and have a look at the original paper, because there is now absolutely the same content, but now presented in a different style, in a different form. So I just want to show you. Here in the paper, they have this 5-step process, and this is here classification, criteria, identification. Classification criteria embedding structure with a concatenation, of course. Then criteria compression via the clustering. You remember the cosine distance here. And we have here, you would go with UMAP, of course. Then we have the rubric generation, clearly bottom-up approach or clearly top-down approach. And then you have the pattern analysis. Great. That's it. Now what we achieved, what is so special? Why should you think about this? It is not just the best overall strategy, but we built something that is context dependent. Because optimal strategies vary by the given task. Whatever your task is, there's not a general solution for all the domains and all the possible solution and all the possible boundary condition to solve your problem. So, context dependent. The second is it's a dynamic adaptation. You really adapt to this new task, to this new query by generating now task-specific criteria. Let's say user understanding for instruction following. And hopefully you're being that general, you can eliminate some human bias. Because if you have defined as a human, hey, this is strategy 1, this is strategy 2, this is strategy 3, you have to follow 1, 2, 3. Maybe you thought that this is the best solution, but it turns out for a particular problem, this is not the best solution. Let the system, the AI, optimize itself. Visualization. If you come here to my channel, Discover AI, we're gonna have a simplification. Here's it. So we have a target LLM. Let's say this is our R1, reasoning 1 model that generates here the reasoning traces. And then we have a second AI, a second analysis LLM In the study, they used the GPT-4 Omni that looks now at the generated reasoning traces from R1 and tries to analyze the reasoning traces, tries to find pattern in those reasoning traces of R1, tries to find now whatever. So this separation, if you want, ensures the framework remains model agnostic. You can exchange here R1, GPT-4, you go with a Q1, whatever you have access to, and it is scalable. As I told you, the target LLM generates here the initial chain of thought reasoning traces. Analysis LLM acts now as a kind of an intelligent analyst. Brainstorm criteria for chain of thought traces, identify now the strategy used in R1 from its pre-training data, like inductive, deductive, generates rubrics to classify the strategy, remember top-down, and labels now the new responses by matching them to the rubric categories. So we have kind of a register built up of all the reasoning strategy that we develop, and we can see and identify. Careful. Be on the same level. It doesn't make any sense if you have an R1 model that generates highly complex reasoning traces and you go in with the analysis LLM here with a tiny little bit, I don't know, 0.6 billion free trainable parameter, 2-bit quantized model. It will not work. You have to have here eye level. The system have to understand, have their own pre-trained capacity for complex reasoning. Now remember, this second AI does not generate any answers, no? It just, now interesting, it reverse engineers the reasoning pattern from R1. Just want to understand the functional, the basis functional of the generator of reasoning traces in R1. Great. This is now officially the end here of the paper that I wanted to present to you. Have a look at this. It is beautiful and maybe something happens to you. And yes, it happened to me. My brain continued to work after reading this. And I thought, hey, so it's only about CoT Encyclopedia. If I combine this with DSPy, can I have a little bit more fun? Oh yeah, let's have a look at this. So my idea is simple, basic. Chain of Thought Encyclopedia analyzes here the emergent reasoning strategies from R1 or R2 if you watch this video and it's already out. DSPy is kind of engineering them up front, no? So what we have now, a loop. I see DSPy more and more as a flow something, a flow code design of initial prompts. But it does not really understand why something is happening. An optimizer is using here with a metric here an accuracy performance indicator. Great. But I want to have, if you want, a semantic understanding why a particular reasoning trace fails. You might say, yeah, you cannot apply thermophysical laws here if we are not in an equilibrium or if we have a chaotic system. You cannot go with a linear approximator to chaotic system. Or, I want to understand the deeper reasoning, why some diagnosis fails. And if some new strategies are suggested with this encyclopedian knowledge, I want to understand why. Where does the idea come from? So if we have now DSPy flow, and then we have the Chain of Thought Encyclopedia, and then we have a re-optimization here of, let's say, only the prompts. We don't want to modify here the tensor weights here with a fine-tuning. Just a simple DSPy is for simple people like mine. The DSPy flow re-optimizes now. This is now, I think, something absolutely fascinating. And you know what? My thinking didn't even stop here. No. We have a target LLM and an analysis LLM. The target LLM produces here our complex reasoning traces. It wants to solve the given query, my task. So, prints out here the reasoning traces. The analysis LLM gets those and analyzes them. Now just imagine that in a particular domain, let's say theoretical physics, chemistry, whatever, quantum mechanics, quantum field theory, and whatever, we have now reasoning traces. Solution, mathematical solution, physical solution, chemical solution, biomedical solution, pharmacological solutions, whatever, or financial solutions, medical solutions. And we have here kind of a register somewhere, let's call it a reasoning strategy register. And whatever the LLM here analyzes and finds, it doesn't just analyze, but it says, you know what, I just write it down so I know what I already analyzed and what I judged it. Hey, this was good for this particular task, or hey, this methodology was successful for this boundary condition. We just build a register, a reasoning strategy register. And then, we have a simple, MCP client-server architecture. We just have a data transfer. Great. But you know what's interesting? If the analysis LLM says, it looks like the target LLM provided such a complex reasoning trace to me, I cannot get it. I'm not intelligent enough as a little GPT-4 Omni to really understand the background reasoning, what's happening, how to find a solution. It can simply go here, MCP, A to A, reasoning strategy register, look up and says, hey, wow, I found a new, in the simplest case, it's a template. It says, look, I have 12 steps to perform, and then I understand why this reasoning is happening. So what we have now the data, and guess what? GPT-4 Omni is a closed model, so I cannot fine-tune it, but I can use in-context learning. Let's say with this reasoning strategy register, I have few short examples, maybe 2, 3, 5, maybe 10 examples, where I can download them now too, and in a prompt and in-context learning for a closed system with ICL, I now learn the analysis LLM, these new reasoning paths, more complex. And then this analysis LLM can provide now a feedback and understand here, or maybe even help the R1 to further optimize if we do this in a loop. And I thought, hey, wait a minute, I have multi-agents who solve problems for me, no? But I just throw away. If they find solutions, I don't remember them. The AI system doesn't write them down for further use. So what if I have a multi-agent system, let's say on theoretical physics, and I find complex solution to complex topics? Why not feed those solutions into the reasoning strategy register? And maybe they belong to, I don't know, complexity theory, fluid theory, quantum field theory. So wherever they belong to, I put there just a reminder, hey, this was the solution that works for this particular topic. So I have an external structure from my current work that feeds now new solution in the reasoning strategy register. And you see where I want to go with this, no? So my daily work will provide new solution, and then the analysis LLM can also use, let's say this is not an open source, but this is a closed one, can also provide insights with in-context learning prompts to further increase here for the target LLM, maybe the reasoning capability of those target LLM. If you think about it, it is so funny because as I was smiling, I thought, you know what this is? This is kind of a make me clever AI, no? Because this analysis LLM just analyzes here the answer given. It says, this was not really a clever strategy to respond to the task, no? But the more clever this LLM is, and the better the feedback instructions are to the main LLM, the better the complete system will evolve as self-continuous improving AI system. And yes, of course, if I have an R1 system that I have locally maybe here on my computer infrastructure in the university, at home, wherever you are, at a particular time, let's say every month you go and you say, hey, I want to increase the reasoning capability of my local personal R1 system. So I just do, if I have access here to the reasoning strategy register, a supervised fine-tuning step. I don't need ICL to go here. Once a month I say, okay, I invest $5, $10, whatever it costs, and do a short supervised fine-tuning because I have access to these weight structures. So you see, whatever you want to build, I think there's nothing holding you back. Go crazy. Hey, maybe I made a mistake in my thinking here. This is just happening as I read the paper. But I just want to show you AI is amazing if you have a little bit of an understanding, like watching my videos, and you get some ideas. You can build combination that really will improve the reasoning capabilities of your system. So, hey, why not subscribe? And I see you in one of my next videos.